Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back to the Deep Dive. We're here to get you smart, fast, by breaking down the most complex research out there. Our mission today is to deliver those aha moments that really stick. And today, we are going right to the heart of it all, the very center of our own Milky Way galaxy. We're focusing on the biggest, most powerful thing in our neighborhood, Sagittarius A, the supermassive black hole. For decades, the story about SGRA has been pretty simple. It's the ultimate gravitational bully, the inescapable destroyer,
right,
presiding over this chaotic, violent, and just completely unforgiving patch of space.
That's the picture everyone had. A gravitational meat grinder is a term I've heard used, and it's pretty accurate to the old models.
Meat grinder. I like that. But our sources today, and we're talking about a groundbreaking new paper in astronomy and astrophysics, they suggest something else, something almost impossible. A totally different story.
It's a huge shift in perspective.
So our mission is to unpack this new data from a team led by Dr. Florian Peisker at the University of Cologne and figure out why these celestial objects right on the black hole's doorstep are showing such stunning defiance.
And you have to understand, that conventional image, the meat grinder, it was built on solid physics. The whole region is defined by these extreme tidal forces.
Right.
I mean, the assumption was anything that wasn't a super dense, isolated star on a very safe path would just be violently elongated. Shredded, torn apart, consumed. Destruction was the rule. It was expected.
So we've got this historical certainty. Destruction is the default setting. But now, these new findings, they're not just tweaking the model. They're forcing a fundamental rewrite of galactic center dynamics. So let's get into it. How exactly does this new evidence suggest SGRA is, and I'm quoting here, less destructive than we all thought?
Well, the core finding is so disruptive because of what they were looking at. They observed several of what are called dusty objects, these complex bodies that are just shrouded in gas and dust.
Okay, so not solid rocks. These are fluffy, fragile, you'd think.
Exactly. They were the prime candidates for destruction, and yet they're following these surprisingly stable, resilient orbits. And this isn't some, minor correction. It's a foundational challenge to everything we thought we knew. It suggests these objects have some kind of unexpected, built-in toughness.
An oasis of stability in the middle of all that expected chaos. That's the mystery we need to solve. But we can't really do that until we talk about the tech, the monumental leap that lets scientists even see this in the first place.
Right, because observing the galactic center it's famously difficult.
Why is that? What's the big problem?
Well, two things, really. First, it's just incredibly far away. We're talking about 26,000 light years.
That's a big number.
It is. But the more critical problem is that the space between us and the center is it's choked with these huge, dense clouds of interstellar dust and gas.
So it's like trying to look at a street lamp through a fog?
That's a perfect analogy. It's a cosmic curtain. And it blocks almost all visible light. Traditional telescopes are basically blind.
So without a way to peek behind that curtain, we're just guessing. We're running models that predict chaos, that predict things getting stretched and torn apart.
Spaghettification.
Right, the whole 9 yards. But we couldn't actually see it to confirm. We just assumed.
We had strong theoretical reasons to assume, but yes, we needed a way to cut through all that smoke and actually measure the orbital paths with pinpoint accuracy.
Okay, so if distance and dust are the twin problems, what's the solution? What's the piece of tech that finally gave Dr. Peisker's team the clarity they needed?
The solution is this amazing new instrument called the Enhanced Resolution Emitter and Spectrograph. Thankfully, everyone just calls it ERIS.
ERIS. Okay. And where does ERIS live?
It's installed at the European Southern Observatory's very large telescope facility, the VLT.
Ah, the VLT in Chile, in the Atacama Desert. I've seen pictures. It looks like something from another planet.
It's one of the best places on Earth for astronomy. But the VLT is the infrastructure. ERIS is the key that unlocks the galactic center.
So what's its secret? How does it get through that cosmic fog?
It all comes down to the kind of light it's designed to see. ERIS captures radiation in the near-infrared range.
Near-infrared?
Yep. It's a wavelength of light just outside what our eyes can detect. And that is the absolute sweet spot for this kind of work.
So why is that? Why does near-infrared light just sail through the dust when visible light gets blocked?
It's all about wavelength. Think of the dust particles as tiny little roadblocks. Visible light has a shorter wavelength, so it just slams into them and scatters.
Okay.
But the longer wavelengths of infrared light can sort of diffract or bend around those tiny dust grains much more easily.
So it's like a big truck being able to drive over a small pothole that would stop a bicycle.
A little bit, yeah. It allows the light from the stars and hot gas near SGRA to pass through that curtain and reach us.
Oh.
It gives us a clear view.
But just getting a view isn't enough, right? I mean, to see if an orbit is stable, you need incredibly sharp images. You need to see tiny little wobbles from 26,000 light years away.
You're exactly right. And that's the other half of the magic. ERIS is integrated with the VLT's adaptive optics system, AO.
Adaptive optics. I've heard of this. This is the tech that corrects for our own atmosphere, right?
Precisely. Even on the clearest night, the turbulence in our atmosphere smears the starlight, blurring the image.
So how does it fix that? It seems impossible.
It's an incredible piece of engineering. The system uses a flexible mirror, a really thin one, that's controlled by thousands of tiny little actuators. It constantly monitors a reference star to measure how the atmosphere is distorting the light in real time. And then it changes the shape of the mirror hundreds of times a second to apply the exact opposite distortion.
Wait, so it's actively canceling out the wobble of the entire Earth's atmosphere?
In a nutshell, yes. It creates an image that's as sharp as if the telescope were in space. And that stability, that crystal clear resolution, is everything. Without it, you could never measure the tiny changes in the orbits of these objects. The combination of near-infrared vision and this extreme AO stability is why these findings are so solid.
That level of rigor is so important when you're making claims that overturn decades of theory. And it's worth saying, again, this isn't some, preliminary press release. This is a peer-reviewed paper in a top journal. This is tested, state-of-the-art science.
Absolutely.
Okay, so we've got the environment, we've got the tools. Let's introduce the main characters in this story. The study focused on 4 specific objects that have been the subject of a lot of debate.
Right. They are G2, D9, X3, and X7.
G2, D9, X3, and X7. And why these 4?
Because they were all poster children for destruction. The older models basically had them circled in red ink. They were the ones that shouldn't have been able to survive.
So their very existence was a puzzle.
It was. And the crucial point that sets up this whole deep dive is that the new ERIS data definitively refutes those old dire predictions. The spaghettification, the fragmentation, the infall. It just didn't happen.
They were supposed to be destroyed, but they're still there.
They're still there. And they're thriving.
Okay, so let's dig into the most famous one first. G2.
Ah, yes, G2.
It's famous because it gave us a chance to watch this interaction happen in real time, right? Before ERIS, G2 was what everyone was pointing their telescopes at.
It really was. It was the perfect test case for stellar disruption. The common wisdom for years was that G2 was just a pure cloud of dust and gas.
No star inside, just fluff.
Just fluff. It had no significant internal gravity holding it together. And if you're just a loose ball of gas, you have absolutely no way to resist the tidal forces of SGRA.
And it was on a collision course, so to speak.
A very close pass, yes. Its trajectory was predicted to take it through its closest approach, its periaps, at a distance of only about 36 light hours.
36 light hours, that sounds incredibly close.
It is cosmically tiny. That's deep inside the zone where the black hole's gravity just dominates everything.
So the pull of gravity on the side of the cloud closer to the black hole would be way, way stronger than the pull on the far side.
Immensely stronger.
Yeah.
And that's the very definition of a tidal force. That's what leads to catastrophic. The prediction was clear. G2 would be stretched into a long, thin noodle of gas. It would lose a ton of mass, break apart, and we'd see a big flare as the material fell into the black hole.
A spectacular observable death.
Right.
Of the black hole having a meal.
Exactly. Everyone was waiting for the fireworks.
But the fireworks never came.
The fireworks never came.
The ERIS observations tracked G2 as it swung around the black hole, and nothing.
Instead of being pulled apart, G2 followed a shockingly stable orbit. The expected drama was completely, utterly absent.
So what does that tell us? If it wasn't destroyed, the original idea must have been wrong.
It had to be. A pure gas cloud simply cannot survive that. Its own internal gravity would be, orders of magnitude too weak to fight the black hole's pull. It would have dissipated.
So it must have had some kind of internal structure, something strong enough to hold it together?
Precisely. The only logical conclusion from its stability is that there must be a central massive anchor. There has to be a star inside that dust cloud.
A star. So it wasn't a gas cloud at all. It was a star wearing a big, dusty coat.
That's the strong implication, yes. The star provides the gravitational backbone needed to resist the tidal forces.
But if there's a star in there, why is it so dusty? Shouldn't we just see a star?
That's a great question. The idea is that the star is likely very massive and young, and it's surrounded by a very thick stellar wind or maybe an envelope of material it's scooped up somewhere. The key is that the star's own gravity creates this little zone of safety around it, what astronomers call its Hill radius.
The Hill radius.
Right. Inside that bubble, the star's gravity is stronger than the black hole's tidal forces. And for G2 to survive, its star had to be massive enough to keep all that dusty material tucked safely inside its Hill radius, even at its closest approach.
So the fact that it didn't lose any material, or very little, is the proof.
It's the smoking gun. It confirms the central mass has to be robust.
That's a huge conceptual shift. We went from a simple, doomed gas cloud to this complex, resilient object built around a star.
It completely changes our senses of what can survive down there. It tells us that an object's internal structure, its own toughness, is way more important than just how close it gets to the black hole.
G2 sets a whole new baseline for resilience.
It does. And if a single star can do that, it raises the next question. What about something even more complex?
Like two stars.
Like two stars.
Which brings us to D9. This is where things get even stranger. So G2 proved a single star can anchor itself. D9 raises the stakes. We're now talking about the complexity of two stars bound together, orbiting each other right under the black hole's nose.
And D9 is a really special case. It was only just discovered by Peisker's team in 2024.
And its big claim to fame is that it's the first binary star system ever seen this close to a supermassive black hole.
Exactly. And the physics here gets exponentially more complicated. This isn't a simple two-body problem anymore. It's a three-body problem in the most extreme environment imaginable.
Three bodies being the two stars in D9 and the black hole.
Right. You have these two stars in a delicate dance with each other, while the black hole is this massive external force constantly trying to mess with that dance.
It seems like a configuration that's just designed to fail.
Theoretically, yes. The internal gravity holding the binary together is in a constant tug of war with the external tidal field trying to pull them apart.
So the most obvious fate would be for the black hole to just rip them apart. One star goes one way, the other goes the other way.
That's one possibility for sure. But the sources point to something even more exotic. A different prediction.
Which is?
That the black hole's gravity could actually force the two stars together to merge into a single, more massive star.
Wait, how does that work? How does a force that pulls things apart end up pushing things together?
It's a fascinating and counterintuitive process. In astrophysics, it's known as the Kozai-Lidov mechanism.
Kozai-Lidov. Okay, you're going to have to break that down for me.
I'll try. So the idea is that a massive, distant third object, that's SGRA, can seriously perturb the orbit of a tight inner pair, which is D9. It doesn't just pull on them. It causes their internal orbit, the path they take around each other, to oscillate wildly.
Oscillate how?
Over time, their mutual orbit can go from being nearly circular to being incredibly eccentric, stretched out like a rubber band.
So they swing out really far from each other and then come scream back in super close.
Precisely. And when their orbit is at its most eccentric, the two stars pass exceptionally close to each other. This creates huge tidal friction between them, which robs the orbit of energy, causing it to shrink until, bang! They collide and merge.
So let me get this straight. The black hole acts like a gravitational meddler. Doesn't destroy D9 by pulling it apart, but by using its gravity to force an internal self-destruction.
That is a perfect way to put it. The black hole acts as a twisted catalyst.
And this would create a whole new kind of star, right? Something really unusual.
A very exotic, massive, rapidly evolving star. It's a process astrophysicists have been hunting for, and the galactic center is the perfect place for it to happen.
The theory is beautiful.
Mm-hmm.
But what did the ERIS data actually show?
Well, once again, reality defied the prediction.
Didn't merge.
It didn't merge, and it hasn't been torn apart. The data shows that, for now, D9 remains intact. It is a stable, orbiting binary system.
That's incredible. How is that possible?
It implies that the internal gravitational bond between those two stars is just strong enough to resist that Kozai-Ladov meddling from the black hole. Either that, or its orbit is just outside the specific zone where that mechanism really kicks into high gear.
So these stars are just tougher than our models gave them credit for.
Yeah, far tougher. It suggests that binary systems can survive in regions we previously thought were just far too dangerous. It demands a complete recalibration of how stars evolve in these extreme places.
And this theme of unexpected stability, it doesn't just apply to G2 and D9. There were two other objects, X3 and X7.
Right. And while the sources don't go into as much detail about them, their stability is key to the big picture.
How so?
Because it shows this isn't just a fluke. We're not just looking at one or two weird survivors. The fact that you have 4 independent, complex, supposedly vulnerable objects, G2, D9, X3, and X7, all showing stable orbits, that's powerful statistical evidence.
It tells you this resilience is a real feature of the population down there, not just a one-off.
Exactly. It's a population-level trait.
So if you put it all together, the story is clear. All 4 of these objects are, quote, less fragile than earlier models had suggested.
It completely changes our view of that environment. It's not a graveyard for everything but the toughest single stars. It's a more nuanced, maybe even a denser neighborhood, populated by all sorts of structures, including binaries and stars in dusty cocoons.
The census of what lives next door to SGRA needs a serious update.
A total update.
Which brings us to the biggest implication of all, the nature of the black hole itself. So all this evidence of stability painstakingly gathered with ERIS, it leads to one huge conclusion. SGRA is not the simple gravitational bully we thought it was. It's more complicated.
And Dr. Peisker, the lead author, he summed it up perfectly. He said, the fact that these objects move in such a stable manner so close to a black hole is fascinating.
It's a simple statement, but it contains a paradigm shift. The takeaway for you, the listener, is that SGRA's destructive power might have been, well, overestimated.
And that is a massive deal for astrophysics, because if that environment is more stable, it's not just a demolition site anymore. It transforms into the perfect laboratory.
A laboratory for what?
For watching long-term, complex interactions between black holes and stars, we can now study stellar evolution and three-body dynamics over long periods without just assuming everything is going to be destroyed immediately.
So we've moved SGRA from the role of destroyer to something more passive, a stable, if extreme, landlord.
That's part of it, but the research team actually pushes the idea one step further.
Which is... Don't tell me it's actually a force for good.
Not good, maybe, but a force for creation.
Wait, a black hole as a creator. How can the thing that's supposed to destroy everything end up building things?
This is the most counterintuitive and exciting part of the research. It's an idea championed by Mikhail Zajiček at Masaryk University. He argues that the processes there are much more complex than just consume or ignore. In his model, the black hole can actually stimulate their formation or the formation of pretty exotic, dusty objects.
How?
Most likely via mergers of stellar binaries.
So we're back to D9.
We're back to D9 and the Kozai-Ladov mechanism.
So the very same mechanism that was predicted to destroy D9 is also a mechanism for creation. The tidal forces that cause chaos inside the binary are what force the two stars to fuse into one new, bigger star.
Precisely. D9 itself is stable for now, but its existence proves the raw ingredients are there. The model suggests that other binaries with slightly different orbits or separations would fall victim to this process and undergo a spectacular merger.
And the exotic dusty objects we see, like G2 or X7, could be the children of those mergers.
It could be the end products, yes. When two stars merge like that, it's an incredibly violent event. It would eject a huge, dense cloud of dust and gas,
which would surround the newly formed supermassive star,
creating something that looks an awful lot like a G2 type object, a massive star hidden inside a dusty cocoon, born from a process that should have led to annihilation.
That completely flips the script. The galactic center isn't just a vacuum cleaner, it's an astronomical forge, using gravitational stress to speed up stellar evolution in ways that are impossible anywhere else.
It gives us a whole new lens to look through. Now, when we see one of these dusty objects, we have to ask, is that a survivor? Or is that a creation? Is it an old star that toughed it out? Or is it the weird offspring of the black hole's influence?
And the stability findings confirm that whatever they are, they can stick around long enough for us to study them.
Exactly.
So what comes next? Where does the research go from here?
Well, this is just the beginning. The plan is to keep using ERIS to watch these objects. We need more data over longer time spans to see if D9 stays stable forever, or if it starts to show signs of that orbital decay we talked about. We need to track the paths of G2, X3, and X7 with even more precision.
And they're already looking ahead to the next big toy, right? The extremely large telescope.
The ELT, yes. That's the future. It's currently being built, also in Chile.
And it's going to be extremely large.
It is. It represents a monumental jump in light-gathering power and resolution. It will make the VLT look small.
So what will the ELT let us do that ERIS can't?
With the ELT, we might be able to do things like directly resolve the star inside G2's dusty cloud, or measure the tiny separation between the stars in D9. And crucially, it will let us hunt for more of these exotic objects to see if we can find the telltale chemical signatures of a recent stellar merger. It's going to be the definitive tool for figuring out how stars are born, how they survive, and how they die in the most extreme place in our galaxy.
What an incredible deep dive. We started with this simple, almost monolithic idea of Sagittarius A as the ultimate gravitational bully.
It's a great destroyer.
It's a great destroyer. And thanks to the insane precision of ERIS and adaptive optics, that whole story has just been shattered.
The resilience of G2, hiding its star, and the simple fact that a binary system like D9 can even exist down there. It just redefines the entire environment.
We now see the galactic center as this complex region where survival depends on an object's own inner strength, and where stability and even exotic creation are possible.
We moved from a place of pure annihilation to one of robust, long-term interaction. It's a perfect example of how new technology forces us to question what we thought we knew.
So the key takeaway for you listening at home is that the dance around SGRA isn't just about the black hole's power, it's about the resilience of its partners.
The galactic center is a place of survival, and maybe, just maybe, a place of extreme stellar alchemy.
Fantastic. Thank you for joining us on this journey to the heart of the Milky Way. And as always, we will leave you with one final provocative thought, something to chew on. It builds directly on this research. So here it is. If the supermassive black hole is genuinely capable of stimulating the formation of unique, massive stars through these forced mergers, using destruction as a bizarre tool for creation, and if those resulting exotic, dusty objects are stable enough to survive for long periods in that environment, what completely unexpected types of stars unlike anything we see anywhere else, might already be thriving down there, waiting to be discovered, living right in the gravitational shadow of Sagittarius A. The ultimate gravitational mystery just got a whole lot more complex, a lot more fertile. We'll see you next time on The Deep Dive.